Good morning, calculators.
Good morning.
Welcome, welcome. Let's see. Don't want to do that. Sweet. The alternating series is our goal today. Let's get into it. Share a screen. The alternating series. What you say is an alternating series? Let's find out. Let's get a new piece of paper. Let's make it graph paper. I don't know why, it just seems like a cool thing to do. All right. So I hope you were kind of at least paying somewhat attention to the syllabus. So today we are learning something new. Tomorrow we're learning something new. And then on Thursday, we are reviewing for the chapter 10 test. So all of this business about convergence. We really just have kind of two more tests to look at. Today's alternating series to see when those converge to a number despite having infinitely many terms. And then we're going to do the same thing with something called the root test, and more importantly, the ratio test. And then all those tests will be done. We could put this behind us and start kind of seeing what all this will actually do, how this will actually pay off and do something cool. So 10.6, alternating series test. So we agreed earlier in this class that the good old harmonic series diverged. And again, we said just barely, like it was so close, since the p-value, our p-test, since that p-value right there is 1, we said that actually diverged by the p-test barely. And even to the point where if that 1 wasn't a 1, but it was a 1.01, then it suddenly converged. And so this was the line. And so what if I made a slight modification to this? Slight mod by, whoa, that's the worst sigma symbol. It's so ugly, let's leave it. What if I made this slight modification by raising the top to -1, but even raising that to the nth power? This creates what mathematicians call alternating, and you'll see quickly, if you don't already, why this would alternate. So if I stick n as 1 in there, that I'd have -1 to the 1 power on the top, so that'd be -1, and on the bottom I'd have 1. But then what happens when you put n as 2 in? Well, that on top you have -1 squared, which now turns into +1, and then the bottom, of course, would be a 2. And then when you put a 3 in there, -1 cubed is actually -1. And -1 to the 4th is actually +1. And so you have the alternating series. And of course, if you didn't know it before, now you do. What's alternating is actually the signs. So you have a plus and then a minus and then a plus and a minus and a plus and a minus and so on and so forth forever. one more term, that would be a minus. Come on, man, focus. Minus 1/5, and then goes on forever. What's your sense of that? Do you think that's going to converge? And I say sense because we don't really sure, but do you think that's going to converge or diverge thanks to that modification? Well, for the fun of it, while you are contemplating that, why don't we go over and just let Excel. It's slow morning. Our brains are tired. Let's go over here and fire up Excel. See how that behaves. So both of these pass the divergence test, meaning the terms are on their way to 0. And both of these sequences, the harmonic and then the alternating, I guess you'd say the alternating harmonic series, both of those are actually on their way to 0. Let's see, where are you over there?
I would guess it would diverge because it's still going at the same rate, even though it's going from both sides, but that would just be a speculation.
Yeah, and that's what we're doing right now. Anybody speculate the opposite of that? That no, I think actually because 1/n was so close to converging that that minus sign might just push it over the edge. What are we doing here? So let's throw out a few terms over here as we've done in the past. And so this first term would equal negative parenthesis -1 raised to whatever this number is over here. There's the numerator, now the denominator divided by just C3 again. So of course that first one's going to say -1. And then if we didn't screw this up, I guess the next one is +1/2. Okay, yeah, it seems to be working. And then it went to -1/3. So I'd expect this to be -0.333. Okay, that seems to be working. And of course, this doesn't really help us much. Notice as per usual, we're at least watching the terms go to 0, right? And if they are going to 0, we sort of don't care whether they're positive or negative, right? Because they're still kind of amounting to nothing, whether they're taking a little away or adding a little bit, and who really cares? Because they're on their way to 0. So this is passing the divergence test at least. But of course, what we're interested in is equals sum of these two cells. Bam, close the parentheses, go up there and throw F4 $signs onto that. Bam. Now we're saying, okay, after, you start out at -1 and then you add a half. And so now you're down to -1/2. But then you take a third off and now you're down to -0.83. Now we're going to add a quarter. So that's actually going to go up a little bit. And so on and so forth. So if I grab, maybe that's too many to grab. Let's go in and insert just to kind of play with this a little bit. Let's go insert a graph, a scatter plot. I think we decided that connecting them was nice. And that's a nice looking scatter plot. We like that. That's beautiful. So there's the alternating part. We used that word before. Remember when we said it converged monotonically versus oscillation? And so in a sense, this is oscillating, but it's not the same word. Like the reason mathematicians said it's not the same word is the fact that this is alternating by signs. In other words, every other answer over here is positive, then negative, then positive, then negative. That's why they kind of made up a different word. But of course, this is going to create graphs because, at one time you're adding something positive and then you're adding something negative and adding something positive. These are all going to oscillate. Every problem in this section is going to kind of oscillate. Now, again, by itself, we can see the sum is, approaching something, but again, we're not really sure. I mean, Ben's guess was it's still gonna diverge, just because, well, the terms are still kind of getting small at the same speed as the harmonic series. I wonder what would happen if let's try something a little more sophisticated here. I want to see if this influences you at all. If I'm going to go back and make the harmonic series. See, is that working? If I say copy right here, paste this over here. Let's see, that works, except for it's going to be D. We need it to be F3. Let's see, who's good at Excel? Can I add a second graph to the same exact graph? That's what I want to know. Add a series. Can I add one? Series name, I don't care. X values. Those guys right there. Let's see, that didn't seem to like that too much. Not sure I know why. That felt pretty good. It felt like it was working.
Maybe for some reason it didn't expand the axes so you can't see all the points.
Yeah, I think that's all it is. Because notice those values, it starts out at 1.5, then it goes 1.8. Notice the top of my graph doesn't show that. So let's see, let's play around a little bit. Can how do I adjust the size of this? Click over there. Format major axis, format the axis. Right now it's going to 1.5 and we need to go up to like 5. So I think that's the reason. Yeah, I just think we weren't seeing it. Except for that isn't true. Well, in the interest of time, let's just punt and make a new one. I was wondering if it would have helped to have it on the same exact graph, but I guess I don't want to waste any class time. I don't know if that's helpful. The question is, does it, I don't know, I guess, does it look like this is laying, as this rises and rises and rises? Again, I don't think it's obvious. We've discussed this a bit, but is that actually an asymptote? Is this rising in such a fashion that it's actually going to level out at some point against something? And the answer we've decided is no, thanks to the fact that natural log of infinity is still infinity, albeit very slow. So this one actually is not an asymptote. It's kind of like a parabola. Parabolas just get wider and wider and wider. Does this look any different up top to you? Does it look like it's getting there, if you will, any faster? Does it look like it's leveling out more? Let's drag that down a ways. I'm just dragging down the alternating one. What's your thoughts now? I want you to notice something as you look down here. Notice that's 69405. And then the next one goes to 69225. But then notice the one below that, 69404. Because remember, they're still alternating here. And notice one below that is 69404 again. Now, again, there's more decimals after this, right? So that doesn't mean they're now equal. It doesn't mean we've now found the answer. But notice it actually, after 560-ish terms, it actually really does start to seem like it's approaching something. And that actually turns out to be the case. It actually is. That's kind of why mathematicians thought this deserved, if you will, kind of a separate look, or maybe I should say authors decided this deserves a second look. So it turns out that if it's an alternating harmonic series, it really does level out to something. Now, those of you that are, I don't know, true mathematicians by nature might think, well, what's the proof of that? I mean, in the end, you just kind of, and I think to some extent we proved, or at least poofed, that the harmonic series went to infinity. It diverged simply because the natural log of infinity is still infinity. But isn't this kind of the same thing? I mean, does it feel like it requires maybe a proof, some kind of a proof to you? Notice in the end, though, one of the things that's kind of funny, I think I'll get out of this and get back to writing. But one of the things that's kind of interesting about this, if you actually kind of look at the series a little bit shorter, is it's kind of the combination of really two series put together. In other words, you have -1/1 minus 1/3 minus 1/5 minus 1/7 and so forth. So in other words, it's kind of like all the odd powers. Yet all the even powers, if you're to sort of kind of add those on later, are, well, all the even ones: 1/2 plus 1/4 plus 1/6 plus 1/8 and so forth. And really our solution here is actually the sum of those. So one of the things you might wonder that I think is really might be interesting is all alone, I'm just going to ask a couple of interesting questions here. All alone, just the blue series, do you think that would converge? Because aren't the terms, isn't there like less of them, if you will? Does that make sense? There's less of them, isn't there? Because before it was 1/1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and now like half of them are gone. So maybe this now adds up to something. Any thoughts on that? Do you think that sort of, I don't know, I'm making my own terminology up here, but kind of that even harmonic series would converge now because half the terms are gone? Anybody have any thoughts on that?
I'm going to grow slower than 1/x, so probably.
Think about this. So I like what Vale said. In other words, we said 1/x was like the line. And so this would grow a little slower, wouldn't it? Since it's missing half of its terms. And so your instinct might be, yeah, that's a little bit slower. And so, 1/x was the line. So 1/2x. And notice, really, that's what this series is. It'd be like the sum of 1/2, not to the nth power. I made a mistake there. That'd be 2 times n. So 2 times 1, 2 times 2, 2 times 3, that's what it would be. Let's see, we'll talk about the one on the top in just a second. Written in this form, written in that sigma notation, does that change your mind at all?
Yeah, it does not converge, I don't think.
You changed your mind. Why do you say that, Vale?
Because when I was picturing it, I was thinking of like 1/2 to the n or something like that, which definitely does converge. But the constant in front, I don't think should make a difference to whether or not it'll converge. It's what the variable is doing that we care about.
Yeah, notice that I guess I should change to blue. That statement up there, does it make sense? You could actually factor a 1/2 out. Wouldn't it be that? And isn't this still infinity? And so if you have half of infinity, you still have infinity. So again, like Vale, I think my initial gut reaction to that is, not just was, but is that it would converge, and yet it amounts to half of infinity. And in a sense, this is one of the, I don't know if the theorem is the right word, but that multiplier 1/2, I mean, that can just be pulled outside. I mean, that's true of any of these sigma expansions that we have, these A of n formulas. Like if I have 9 times n and I'm trying to add it up, you can just pull those multipliers out, kind of like we did with derivatives. We said, oh yeah, there's a multiplier, it just kind of pops out front, just comes along for the ride. That's true here too. So actually, that chunk down there is still infinity. So sort of half of that's infinity. The question is, what about that negative version? Isn't that like negative infinity up there? So again, I find myself just kind of wondering out loud about that. What about that second series, the one on the top? I only picked the plus one first because I thought it was easier to work with. I'm looking at these negative ones and thinking that's a little more confusing. I wonder if that converges. So the answer to this turns out to be a resounding no, surprisingly. And by the way, with respect to that blue sequence, that means something like 1/100 plus 1/200 plus 1/300 would still diverge. Isn't that strange? Because really what you have is just infinity, but 1/100th of infinity. I mean, add some zeros. That's still on its way to infinity. That's just very troubling, I think. So what about all these negatives? What are those going to be? I can't factor something out, kind of like I could before. I wonder if I could write a, you should find this harder. This is why I saved this till later. Could you write a formula for this? Notice there's always a -1 on top because every one of them is negative. But what's the formula on the bottom? Here it was sort of easy to see that it was times 2 times
2
2
to the n
times 2.
minus 1.
Nice job. Because remember back when we looked at arithmetic sequences, aren't those numbers still growing by 2 from 1 to 5 to 3 to 7? They're growing by 2. You're repeatedly adding 2. That's still multiplying by 2. And Vale's exactly right. All you have to do is just modify that. So when n is 1, I get 2, but if I just take 1 off of that, then that would get it down to 1. When n is 2, 2 times 2 is 4 minus 1 would get it down to 3. And so that works too. Does that help? Does that help to decide if this one kind of goes off to infinity as well, or converges to something? Again, I'm being lazy here by not saying n equals 1 to infinity like I should. Well, think about your laws. What difference does that 1 make right there? Kind of by the comparison test or the limit comparison test, it's pretty irrelevant. It's like the 1 doesn't make any difference because n is going to be thousands. So this is still really, I don't know if you will, similar to or roughly equivalent to by the comparison test. By comparison, I guess you could say, I'll just leave it at that. By comparison, which means that also diverges. So now it's kind of like you have, so we have positive infinity kind of plus negative infinity then, and isn't that kind of what's happening? Does that make sense? But remember, I mean, in a sense, does it make sense that it kind of looks like it wants to be 0 then? In other words, if I have an infinite positive number and add an infinite negative number, then doesn't that seem like it wants to be 0 or like it's actually going somewhere? What did we see a second ago? I'm not going to go back there, but I'm just going to flick back so at least I can see it. We saw it kind of working its way to 0.694 or something like that. It seemed like it was kind of settling in on negative 0.69 or something like that. I didn't take it super far. I don't think you can see this right now because I didn't share the screen, but I'm just dragging it way down further right now. Yeah, actually I went way down to, sheesh, this is hard to see. Down to 1800 and the sum is now down to 0.693. So it really negative 0.693. So it really actually does look like it is converging. And so, yeah, I mean, it actually turns out sort of surprisingly, again, this isn't a proof, but it appears that -1 to the n over n as n equals 1 to infinity is kind of converging to, write that down, lost it, pull it back up again so at least I can get it right. Converges to negative 0.693 since S of 1864 is negative 0.69288. And again, it doesn't really matter so much what the 1800 sums of this add up to. It matters more like that the next one is really similar to that. Does that make sense? Doesn't matter that that sum is an answer. Who cares? It matters that the next one is really close to that. That's kind of the idea. Let's try one more thing. Since this doesn't take long, it might. Again, all I'm really after here is just a little bit of intuition growth on your part. So see these last terms right here. Notice how at 1854, 0.69288, 0.69288, 0.69288, 0.69288. Remember, every other term, they're alternating back and forth. And then look at the odd terms, 342, 342, 342, 342, 342. But see how they're coming closer together? So notice this is 342 and this is 288. So they're getting closer and closer together. Let's drag it down even further since we took the time to come over here. Drag it down to around 3,000 and then we'll give up somewhere in there. It's sort of going really fast. You see how they're, again, every other one looks identical. And I think I can make this a little larger and show these to more decimal places. And I think I'll even add some decimal places. I can't remember how to do this. Is it this? Decrease, add. Notice that shows they're not exactly the same anymore. But do you see how close these last two are? 6933, 69299. I mean, they're like 1/10,000th or 1/100,000th off of each other. Does it feel now like this is converging to something? Even if we sort of can't prove it? So ultimately, really, we have kind of like a version of positive infinity being added to a version of negative infinity, and yet it sort of seems to be converging to something. So the fact that they're alternating actually did fix it. I mean, it did solve that problem. One of the problems this doesn't solve, again, as I've mentioned annoyingly, is we don't know what the sum is. We can approximate it. That's pretty cool. 3,266 terms. We have an approximation that's really accurate. And we can kind of say it's at least 0.693 rounded off now. But in a sense, the ultimate answer is nobody knows. Nobody knows what the ultimate solution to this is. Is this like pi cubed over 17? Is this got some crazy logarithm in it, the logarithm of the sine of pi squared, or something that no one's discovered? Kind of fascinating, I think.
Looks suspiciously like the negative natural log of 2.
Nice. Did you type that in your calculator?
Yeah.
So that's an interesting,
Interesting.
conundrum. And and again, you can see how people would get lost in this. The mystery of we can prove because of the alternating series test that I'm about to write down that this really does converge to something. But again, what does it converge to? And we could get lost in trying to kind of uncover that. And again, I would assume this one is a lot of people have probably spent time with this one. Does that make sense? Because it's I haven't modified it much. It's a harmonic series except with an alternation thrown in there. So it's like the simplest alternating series you can create. And so Google search that a little bit and see if anybody has any thoughts on that. See if, because I actually don't know. Has someone actually found it? And maybe like Ben said, maybe it is natural log of 2 or something like that. Again, because of natural log being involved, we wouldn't be surprised if it was involved somewhere. So maybe someone does know the exact answer to this. Do it because you're curious, but I will give you points at the end of this class if you end up close. Actually, I have a note in my, no, I'm not going to say that. Leave that on the table. So here's the deal. The alternating series test. Basically says this: 1, if AN is on its way to 0. Can I just write that in that simple language? That just means the individual terms are on their way to 0. That's a duh. That's the divergence test. The terms have to be getting smaller for this to work. Individual terms have to go to 0. And it also needs to be true that AN plus 1 is less than AN. Do you understand why those two statements are different? In other words, one can be positive, one can be negative, and that's kind of the problem here. Because like, if you have -9, that seems like a big number, but it's negative, whereas if you have 2, your first reaction might be, oh, -9 is bigger. Well, no, it's actually smaller by definition because it's negative, right? So because this world has positive and negative numbers in it and so forth, you just got to be a little careful. So basically each term is getting smaller and smaller and smaller, irrespective of its sign, I guess is really what I'm getting at there. And kind of finally, each term alternates, plus, minus, etc. Hence, it actually will converge. Any series, as long as the terms get smaller, any series, if the terms get smaller and they alternate, it's going to converge. Now, there's a fine point to this. There's just a little bit of terminology. I guess I'll throw it in right now because this is in your assignment. I guess I haven't figured out a ton of significance to this. There's absolute convergence, and there's also conditional convergence. So you have assignment questions. Well, they'll say, does this converge absolutely or conditionally? And usually when mathematicians come up with terminology like this, it's because they think, this is important and it deserves a name, right? And that's what it comes down to. What's absolute convergence? If I asked you to, let's keep this really simple. If I asked you about this series right here, remember, it doesn't really matter where you start, but I'll just start at 1. Because of the p-series test, we say that converges all by itself, right? Like it doesn't need to alternate to converge. It already converged on its own, right? So who cares if it alternates or not? So if I come up here and I throw a -1 up there and now make it alternate, so this is the part that makes it alternate, then that's considered absolute convergence, just because it would have converged anyway. Who cares if there's a negative sign? It just converges faster now. Does that make sense? Because it's going to oscillate. It's going to get bigger, smaller, instead of just growing its way up to a number. So by the p-series, it would have converged without the -1 to the n. In other words, that's the idea there. Whereas, perhaps you can read my mind here. What am I going to say next? Can you make up a series that would not have converged by the p-test? If I make up a series that what doesn't converge by the p-test, n to what power? What's an example?
0.5.
Yeah, like 0.5, anything less than 1. So I could say 0.5, and maybe I'll even write that as the square root, just since you happen to choose such a nice exponent. And remember, that's the p-series in disguise, right? Because that's n to the 1/2 power. And so that would not have converged, right? We would have said this diverged, unless you come back and say, nah, let's raise it to the n power. And by the way, there's no magic to that. Like I could have even said n+1. Does it make sense? That wouldn't have mattered. Doesn't really matter what I put there. Could it be n+7 for that matter? Now, interestingly, though, it does affect the final answer, because now our first term is actually positive. Does that make sense? Because when I put 1 in there, I'd have -1 to the 1 + 1, or -1 squared. And so the first term would actually be positive. So that means back here earlier, when we wrote this sequence out, if I had made up, I'm going to erase this, but if I'd put a +1 there, does it make sense? This would have been a +1 and a -1/2 and a +1/3 and a -1/4 and a +1/5 and so on and so forth. And so we would have gotten a positive answer to this question instead of a negative answer. So it changes the answer, but it doesn't change the fact that it alternates. So that's just kind of interesting. You'll see that in your assignment some, but it's sort of irrelevant ultimately. So would you agree now, based on the alternating series test, since we do still have the individual terms on their way to 0, 1 over the square root of n is on its way to 0, and each term is getting smaller and smaller and smaller, and they alternate. Let's write out a couple of terms of it just for the fun of it. So we'd have +1 over, I'll go ahead and write the square root of 1, even though that would be 1, of course. And then you'd have -1, because when n is 2, you'd have negative. I'm sorry, I forgot the negative sign. This doesn't work if there's not a negative there, right? So you'd have -1 to the third, which would be -1, and then that'd be over the square root of 2, and then you'd have +1 over the square root of 3, and then you'd have -1 over the square root of 4, and so on and so forth. So it's alternating, and the terms are getting smaller, so that's actually going to converge thanks to the fact that it alternated. Does that make sense? So by the p-test, that would not have converged, but now thanks to the fact that it alternates, that alternation allowed it to converge. So that's considered conditional because it has to be alternating, otherwise it wouldn't have converged.
I have a question about the second step of that test.
Yep.
You said a sub n plus 1 has to be less than a sub n.
Yeah, what's that mean?
Well, then the second term in our first one was 1/2, but the first term was -1, right?
Yeah, so n is the previous term, and then when you go n plus 1, that's kind of like the next term. And what was your comment on that?
Well, wouldn't, if the first term's -1 and the next term 1/2,
Yeah, in other words, this right here. So you're thinking of this back here, right?
yeah,
So are the terms getting smaller? Well, they are numerically, but isn't this is your point, isn't this bigger than that? I mean, the number -1 is a big number relative to 1/2, but it's negative. So doesn't that make the 1/2 bigger? Is he right?
yeah.
He is right. What modification, if I only want to talk about the size of the numbers, let me think about this. Let me see how this is worded in the book. My gut reaction is to say, I'll just think out loud with you here a little bit. My gut reaction is to say, oh, okay, we need to throw some absolute values around those. But then if I do that, isn't this now the same statement as the one above it? Follow what I'm saying there? I'm gonna take a quick look at the book. See how it words this. I'm looking in the book and yeah, those aren't there.
What I saw in the convergence sheet test is it actually like separates that AN from the alternating part of the series. So it's like that part without the negatives when they like to they describe it.
Yeah, so let's take a look at this. Converges as long as all the terms are bigger than 0. All the terms are bigger than 0. They're always bigger than 0. And the next term is always smaller than the previous term. So what did you mean by separation, Ben? Because I think you're on it.
Oh, when they show it right there, they have the AN separate from the -1 alternating.
Exactly right. So that's true if you separate out. In other words, the AN is the part that doesn't have the alternation. Does that make sense? So that's a good caveat. It was kind of, your question was a good one, Thomas, because my first thought was, hey, you're right, that doesn't make sense. So that is only if. So as an example, then just to put it down here, the AN down here is just the 1 over n squared part. The alternating part is not part of it. That's the idea. Same thing over here. Here, the AN is just the 1 over the square root of n. So it doesn't include the alternation, doesn't include the sign.
Hey Doug,
Yeah, go ahead.
I guess my question is, this might be a dumb question, but why do we even need that rule then if it only applies sometimes? I feel like the first rule would take care of it.
Yeah, in other words, you're talking about these two?
Yeah, like if it goes to 0, then that basically covers it, right?
Yeah, it's funny that you said that because right after we sort of agreed that, oh yeah, AN is not including the individual term, then doesn't that just take care of it? Yet the, kind of the book says no, like it says no. And again, notice they're being a little more precise than I am, which is good. I'm kind of balancing precision with intuition. They're saying the limit of the individual terms as n gets bigger and bigger is on its way to 0. Do we need both of those? Can somebody, is that just redundant and dumb? Again, your gut reaction should be, well, probably not, because I stole this little cheat sheet, if you will, out of the book. So somebody put a lot of thought into this.
My gut reaction is that even if there's an asymptote at 0, it depends on how fast the equation is approaching that asymptote.
Yeah, the answer to that question is, what if your first term started out 8, and then your next term was 7, and then your next term was, say, 5.8? They're getting smaller, right? And again, let's put 1 over them. No, let's not put 1 over them. Let's just leave it alone. It's like those terms are getting smaller. Would you agree that, if you will, satisfies this condition up here? Hey, look, the terms are getting smaller, right? But what if you keep looking, what if it ends up doing this? What do you see happening now? Well, notice they're getting smaller. But are they on their way to 0? No, they're on their way to 5. And if you're going to add them together, then they have to be on their way to 0. So my gut reaction, Becky, was just like yours. Like, isn't that redundant? But it actually isn't. So they're saying each term has to get smaller, and they actually have to make their way to 0, both.
Well, that's what I was saying, is the only rule it seems like we need is it needs to make its way to 0.
There we go. In other words,
Not the other
you're
way around.
saying this is the only one we need. We don't even need that one. So why would they be adding that one? They don't need to get smaller. They just need to be on their way to 0. And by the way, let's see. Clean this up a little bit. Why do we need that statement? Why can't we just say the terms are on their way to 0?
I wonder if it would like mess up the formula somehow by making it, if it was negative, I don't know if that would mess it up somehow. I don't know.
I've been kind of staying silent because I'm a little confused, but isn't n plus one what we were looking at, which is the negative, and that is, oh, that's not great. Okay, never mind.
Yeah, so they're saying like the alternation over here, this is Ben's observation, the alternation kind of takes care of itself. So there's the alternation, so I'm ignoring that now. And then now I'm just looking at the individual terms. And the alternation is there, you know, as they said over here, this only applies to alternating series. The terms have to alternate. This is what's causing the alternation. So we're ignoring that now. And now let's just look at the terms. And again, those terms are like, well, what we saw at the start, 1, 1/2, 1/3, 1/4, 1/5, 1/6. We're ignoring the plus and minus signs. We're just looking at the individual terms and we're seeing them get smaller.
I feel like this made more sense to me until we started really, really looking at it.
Well, I will say in a simple sense, if the terms are going to zero and they alternate, yeah, you're there. Well, let's leave that for a minute so we don't run out of time. Let's look at a couple examples and maybe one of you will have a brainstorm on that. Because to Connor's point, this actually isn't hard. So this is not a question I'm asking on a test. I'm not going to ask about absolute and conditional convergence on a test. I don't see that that's necessary language, but I can see why they came up with it. So as I look at these terms, as I look at the terms kind of in this sequence, yeah, square root of 2 is a little bigger than square root of 1, square root of 3 is a little bigger than square root of 2, square root of 4 is a little bigger than the square root of 3. I can see these terms are getting smaller and smaller and smaller. Again, I'm ignoring the plus and minus signs. Those are taking care of themselves. And these examples, these simple examples, perhaps, maybe we sort of don't need both. Maybe that's one of those exceptions to the rule. If you come up with some crazy example, well, let's just play with a few crazy examples, or I wouldn't say crazy, but just some examples, kind of like you might see in your assignment. And then we got to look at estimation. So I'm afraid we'll run out of time. So let's try this one. This one might help explain it. I'm not sure. Let's think about this. Example 1, what if I said, let's add up these? And I want you to stare at this for just a second. 3n plus 7 over 5n minus 8. Think about that for a second. Notice it's not alternating. So we collectively said this is our an. I'll write this one correctly this time. What is the limit of an as n goes to infinity? What do these terms become? When you're way out there, when n is 50,000.
Just 3 times infinity over 5 times infinity.
Which reduces to what? Because you're right, the 7 and the 8 don't matter. What does 3n divided by 5n reduce to?
0, I think.
Yeah, I know. I don't think this is obvious yet. I'm glad you said that, because the question is this on its way to 0 or not?
No, it shouldn't be.
Keep in mind, this is not the same as 3 over 5 to the n. That's a geometric series. So you're taking 3/5 of 3/5 of 3/5. That's getting smaller and smaller and smaller. If you take 3 times 1,000 divided by 5 times 1,000, you get 3/5. If you take 3 times 1,000,000,000 divided by 5 times 1,000,000,000, you get 3/5. This, not obviously, I think, is on its way to 3/5. Like those terms are not making it to 0. This is kind of like what I showed a minute ago. Early on, the 7 and 8 are going to make a difference. But later on, way out there, when n is 1 billion, it's not going to make a difference. But again, it would be nice to kind of show this in Excel. These terms are actually on their way to 3/5. They are not on their way to 0. So therefore you're not adding 0 each time. Like we need this to be 0 in order to have any shot at this converging. That statement right there does not pass the divergence test because the terms aren't on their way to 0. So the important
Right.
things here, not
Doug?
0. Go ahead.
I guess my real question is it possible for the terms to be on their way to 0 and also not satisfy the previous condition, which is that each term is smaller than the previous one?
So we understand Becky's question. I think it's a good one. Like, could they be on their way to 0 and yet not be getting smaller? Isn't that what the previous statement said? I think that's what Becky's
Shouldn't
asking.
you be getting bigger towards 0? So if you're like in negative numbers.
Yeah, maybe negative numbers would mess that up somehow. Because what Becky is asking and Raymond is commenting on there is kind of like, is there an example? Can we make up something where they were on their way to 0 and yet not getting smaller? So like maybe, but again, I think the negative number thing is kind of the problem, could be the problem there.
But when we tried to use negative numbers before, it messed up that rule.
Yeah, but that's separate from the alternating part. Like what I'm going to do here in a second is come back to this problem and say, hey, let's take this thing and multiply it by -1 to the n plus 1. And let's like, now it's alternating. And so that's going to create, it's going to create its own set of positives and negatives, if you will. But as a for instance, so, and again, I'm kind of thinking out loud with you here. What if you had, there's the alternating part, but then over here you had like a geometric sequence? Would you agree that -2/3 is also going to do its own alternating now? Because when it's to the 1, then this will be a negative number, but then when it's to a 2, that'll be a positive number. And then when it's to the 3rd, it'll be a negative number. So it's almost like now the negative signs are maybe a little screwed up. It isn't just the examples I started with were, the alternating part was automatically the whole thing that caused anything to do with signs. But early on that would get screwed up. That's kind of what I'm wondering if, so it feels as though that rule is a technicality. Like for instance, right here, in this example right here, when I pick n as 1, does it make sense that the denominator 5 times 1 is 5, 5 minus 8 is a negative number? So you're going to get a negative number down there, but that only happens at the first. And then once n is 2, then all of a sudden that number will be positive from then on. So it may have something to do with the signs, a technicality.
Well, then doesn't that still break the rule, even if it's only the first one?
Well, and there is a point, and I can't remember if it said this in the sheet. I just didn't say it because it didn't come up yet, but doesn't say it here, but it says it in the book. Here it actually even contradicts in a sense what the book says, because it says for all n. It says for all n's. In the book it says after, I don't know, I'll just write it in English, after some point. In other words, in the beginning it could be weird, but after some point it settles into a routine of getting smaller, 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 which I think is actually kind of makes more sense. So would you agree if I threw a 0 in there, made that -80, that's going to kind of screw this up for a little while, because the bottom number is going to be negative for quite a while. Once n makes it to 16, then all of a sudden 5n would be 80, and then you have 80 minus 80 to have 0 on the bottom. And so it's like suddenly there's this screwed up number. So I think it has to do with that. Let's just write out a few of these terms just to kind of, I don't know, do this
I
manually.
kind of hate that caveat because it's not absolute.
Right, that's exactly right. So if I put n as 1 in, I get 10 on the top. If I put n as 1 in, I get -3 on the bottom. And again, this is without the alternating sign part. Maybe I'll come back and put that in a second, but right now I'm just staring at the an part. And then when I put 2 in, I get 6 on 6 plus 7 on the top, I get 13, which is still positive. And on the bottom, what used to be negative is suddenly positive. It's 5 times 2 is 10, 10 minus 2, 10 minus 8 is 2. And so does it make sense that first term is way less thanks to the negative sign? You see the concept there? It's like way less because of the negative sign that just happened. Well, now the negative sign is gone and gone forever. So now what happens? Well, put n as 3 in, you get 16 on top. N as 3, you get 7 on the bottom. N as 4, you get 19 on top. N as 4, you get 12 on the bottom. Do you see how the terms are starting to get smaller now, if you will? Like they seem to be like 13 over 2 was a pretty big number. 16 over 7 is roughly 2. 19 over 12 is kind of on its way to 1. The next term when n is 5 is 22 over 25 minus 8 is 17. Is that right? 25 minus 8 is 17. Doesn't seem right. So see how that negative sign kind of screwed it up in the front? I think that's what this is getting at. And had I made that number on the bottom not -8, but -81 or something like that, it would have been screwed up for a long time until then it finally settled into a pattern. Can you see now that this is, even without the alternation, scoot you over a little bit. Can you see that this is on its way to, well, 3/5 now? I don't think we can see it yet because 22 over 17 is still over 1. But if I keep going out there to like n is 12 or something like that, 3 times 12 is 36 plus 7 is 43. On the bottom, 60 minus 8 is 52. You get 43 over 52. See how it's like less than 1 now? Can you see the terms on their way to 3/5 here, at least a little bit? But it was screwed up in the beginning. So I think in its basic element, this is simple, but negative signs can kind of screw this up a little bit. So the terms don't go. So although these alternate, if I go back in now and throw the alternation in this first one, when I put in as 1 in, would actually be positive. So I'd be throwing a positive in here, in other words, leaving it alone, whereas I'd be throwing a negative in there. So that would become a negative. I'd be leaving this one alone as a positive. I'd be changing that one to a negative. I'd be leaving this alone as a positive and so forth. If I come back and kind of add that element to it. So the individual terms are getting smaller, but they got to go to 0. Like that's actually the more important one. They don't go to 0. So this is an alternating series, but the terms don't go to 0. So this is going to diverge as a result of that. Let's look at some more examples. We gotta hustle here a little bit. What about this one? What if I said something similar? Let's throw a 6 in front of this and let's make this a negative. Let's use k this time. K equals 2 to infinity. Do you see that the alternation here is going to be caused by the -3/4? You don't always just have to have a -1 sitting out there to cause it. Do you agree from previous discussion that the 6 kind of could just be thought of as left till later? And in our case, we're not actually trying to find the answer to this. We're just trying to decide if it converges or not. So if it converges to something, then 6 times it still converges. If it goes to infinity, multiplying it by 6 doesn't change it. It's still infinity. It's like the 6 doesn't even make any difference here. That's just kind of interesting, I think, to note. But again, let's slow down a little bit. What are the terms? Well, notice I started at 2, so I could say 3/4 squared. Well, that's a negative, so that'd be 9/16. But then when I cube it, the negative number cubed will be negative. And so this is going to be negative. 3 cubed is 27, 4 cubed is 64. When I raise it to the 4th power, 3 to the 4th is 81. 4 to the 4th, I think, is 256. I will not trust myself all of a sudden. Should have trusted myself. And then 3 to the 5th, because you're raising it to the 5th, you're going to get a negative. And then 4 raised to the 5th is 1024. So clearly it's alternating. Check. Second, again, to keep it simple, are the terms getting smaller? Are they on their way to 0?
Yes.
Yeah, they are, because 3/4 of 3, I mean, you could turn those into decimals to watch them happen, to watch this happen. But just in a glance, 9/16 is around a half. And by the time you get to 243 over 1024, that's roughly 250 over 1000. That's down to a quarter. So it went from a half to a quarter. And notice again, I'm ignoring the individual, I'm ignoring the negative signs and just looking at the numbers themselves. So AN is on its way to 0. So this actually will converge. Do you recognize this, however, as a geometric sequence? And therefore, not only does it converge, but this is one of the rare cases where you could actually answer the question. What does it converge to? Let's cheat, given that we're getting close to test time here. Let's erase all of these notes since it makes it hard to read. Notice if you recognize it's a geometric sequence because each term is 3/4 multiplied by the previous term. So that's your R value. In the language of this section, that's kind of your X value. Notice this is what it converges to. Notice what those are. What's A? A, oh, that's that number in the front. For us, that was 6. And for us, X was 3/4, right? Well, actually negative 3/4. And it says it converges if the absolute value of negative 3/4 is less than 1. Yeah, 3/4 is less than 1. Our multiplier is 3/4. And so there's my formula. A, which is 6, over 1 minus a minus 3/4. Interesting.
Unknown caller.
Goodbye, unknown caller.
So in this
So-
part, do we have to make sure that it goes to that k equals 0, so it matches our?
All right, yeah, we do have to be a little careful here, don't we? Because I thank you for pointing that out, Ben, because I would have blown over the top of that and screwed that up. So this only works, and this again is kind of why I showed you this the way that I did. It might be better to do this manually. We have 2 choices now. We're either going to have to do it manually to answer it, or we're going to have to somehow get this thing to start at 0 instead of at 2. Anybody have a modification for that? I got to think about this. It doesn't come automatic for me. So I've got a 6 here and I've got a negative 3/4 to the k, but I'd really like this to start at k is 0. Well, this is our first term, right? So how are we going to get that first term to be, how are we going to get that first term to work out correctly? and B 9/16. Who's going to save us?
So are we
Just-
trying to make the equation equal 9/16 or the 9/16 equal 1?
We're trying to make this statement starting at 0 to produce the same exact sequence, 9/16. And I included the 6 here, so I probably should at least put a 6 out in front of it, even though we didn't have one out here. So over here, I could sort of go back and say, you know, this whole thing is times 6 when we're done.
Well, -3/4 to the 0 power is 1, so you could just multiply by 0.5.
You're going the right direction. So the problem is if I did put K in there, this is what Connor's pointing out. If I put K in there as 0, then I'm not going to get 9/16, right? So would it be okay then to, well, just multiply by 9/16 to fix that? Does that work? It does. In other words, we're missing 2 of our terms, right? And 2 of them was 3/4 times 3/4 or 9/16. That actually does fix it. So from our cheat formula, we'd say A, which we now know is that collectively, that's kind of our A, our multiplier up front, so that's 54/16. Over 1 minus our value. So let's see, that'd be 54/16. 1 plus 3/4 would be 7/4. But if we're dividing by 7/4, that'd be multiplying by 4/7. This 4 cancels with that, so we get 54/28, which is 27/14. So not only does that converge, it converges to 27/14. We actually know the exact answer to that. I think your book assignment does not start at 2, so I think it starts at 0, but that's good that we saw that, just because you do have to, if you're going to cheat, if you're going to kind of use the cheat formula, which again, perhaps you can see why I don't like it, because don't you feel sort of not very comfortable with what I just showed you? It's like I'm using a formula I don't feel like I understand very well. Like I'd rather just write these terms out and notice that, hey, look, every single time I'm multiplying times -3/4, and so couldn't I just do this myself, do this manually? I like that better. We're going to run out of time, or I would take the time to do that, but I'd encourage you to do that. Let me show you one other one really quick. We got to look at one other quick thing. Example 3. What about this one? What if I had K squared over the square root of K to the 5th plus, I don't know, 8? What's your gut reaction to that statement? Notice I have not stuck anything in about alternation yet. I will in a second, but let's keep this simple and start from 1 to infinity. Would that converge by itself? Do you see this as both comparison and a p-test?
It doesn't fail the p-test.
Yeah, it fails it because the square root of K to the 5th is 2.5. In other words, this is roughly equivalent in the comparison test, since the 8 doesn't make any difference, to K to the 2nd over K to the 5/2 or K to the 2.5, which means it's roughly equivalent to 1 over the square root of K, or K to the 0.5. So it fails the p-test. So by itself, this would have diverged by the comparison test. That's kind of good practice for. So if it if I go make it alternate now, then it will converge. Does that make sense? If I go make it alternate now, it will converge, won't it? Because the terms are still getting smaller. But we would say technically it converges conditionally, like it has to alternate, because right now it's not going to converge. So if I go back and I do this, I'm going to do something kind of weird, and we'll fix it for a second. But if I throw in -1, what if I raised it not to the k power, but to the 2k power? What does that do? Think about k is 1, k is 2, k is 3.
So it would converge faster.
Yeah, think about what that is. What happens if you put k as 1 in there? What's -1 to the 2 times 1 power?
They're gonna all be positive, right?
Yeah. Because that's -1 squared. That's +1. What if you put k is 2 in there? Well, now you have -1 to the 4th. That's still +1. In other words, the 2 doubles every number. So therefore, they're always even numbers. And when you raise them, does it make sense that doesn't alternate? So if I threw that in there, like the book will, I'm warning you, because this feels like a trick question to me. I don't like trick questions. It's kind of like, oh, look, -1 up front. It's alternating. Awesome. This is going to alternate. Well, actually, because of the 2k, it doesn't alternate. And it actually is doing nothing. It's making it 1, 1, 1, 1, 1 every single time. So that's kind of tricky. Again, I would never put that on a test, but I just happened to see that in your assignment. So what if I go do this now? Now it actually alternates. The terms are getting smaller and they're going to alternate. Boom. Even though it wouldn't have passed without the alternation, this, if we want to be really technical about it, we could say it converges conditionally. And now it met the condition since it alternated. No trick questions. Okay, I got to show you one other thing. I don't think this assignment is terrible. Like I think you'll feel okay about this. I would highly recommend you go do this like tonight and ask me questions at the start of class tomorrow if you feel like you've been thrown a curveball in that assignment. Here's something really cool. So it turns out that in alternating series land, there's a really cool shortcut for estimation. Remember, we like to know, we often can't know the answer to what these add up to, even though, like the example I just did, we say, hey, look, that converges now. Cool. So what is an answer? What's the answer to it? What's it converge to? And we say, darn, I can't know. But could we add enough terms to get it as accurate as we want? Well, here's something that's amazing about estimation. I'm kind of running out of time here. So Rn, which we said was our remainder. And do you understand the concept of a remainder? In other words, I added up the first 20 terms and I'm tired and I just quit because I can't do this anymore. And so then I'm wondering, well, what's the remainder? Like, what have I not added, and how's that going to change my answer? Remember, that was fairly complicated in a previous section, but in this section, it turns out that that remainder will always be less than the next term. That's all you have to do. The very next term, your remainder will be less than the next term, and you could just quit. Now, again, I don't have time to kind of prove this, but if you're alternating, the actual sum gets a little bigger and then a little smaller and then a little bigger and then a little smaller because the terms are alternating, right? But the terms are getting smaller and smaller and smaller. So since they're alternating, that means the very next term will actually be kind of bigger than all the terms after it, if you will. And so that makes this process super, super quick. So and really, this is like, the next term after you quit, if you will. So I don't know, let's just look at an example. So what if I said we have the expression 4 times -1 to the k all over k cubed. Do you agree just by inspection that that would actually converge absolutely? Like we don't even need the alternation for that to converge because it's 4 over k cubed. The -1 to the k just causes the plus and minus signs. So that would have converged even if it wasn't alternating. Does that make sense? But it does converge, but what does it converge to? So we say, okay, well, let's kind of, I don't know, add that up to something and see what we get. So we say we'd like to keep our remainder less than 0.001, let's say. In other words, all right, we'll never know the answer to this, but I'd like you to go add up the first, 20 terms, 30 terms, 40 terms? Like how many terms do we need? That's what we want to know. So the question is exactly that. Well, how many terms do we need then? We need k to go from not 1 to infinity. We want it to go, to some number, and we want to quit. Does that make sense? Because we can't add them all up. We don't know the answer to infinitely many of them. So we'd like to add from 1 to 80, 1 to 90, 1 to 7,000. I wonder how many terms we would need here to get this to work. Well, remember that the an part of this is the 4 over the k cubed part. Does that make sense? Not the -1. It's not the whole statement. That's the an. The -1 to the k is just the causing the alternation. So looking back then at this statement back here, my remainder is less than the next term. Well, aren't we saying that our remainder is supposed to be this, and we want that to be less than our next term, a to the n plus 1. Well, that would be 4 over n plus 1 cubed. Like I'm just replacing k with k plus 1. In other words, just the next term. Again, I hope you're not troubled by the fact that there's k's and n's in this. Only because if I went back here and said k here, k equals 1 to k, like you kind of can't use the same letter twice there, but it's sort of, so okay, I get that. But then when you throw n in there, then it's kind of like, what? But n is a finite number is the point. Like we're going to stop somewhere. Where are we going to stop? K equals 1 to some number. So n for number. Well, all I got to do is solve this. Do you see that all I've done really here is just really replace everything I know in that formula? Solve for n. That's it. Let's see if I multiplied n cubed. Let's go slow here. N cubed to this side. Notice I put an equal sign there. And it's technically less than or equal to, but I did that consciously. Then if I divide by 1/1000, 4 divided by 1/1000 is 4,000, isn't it? And again, I probably should be a little more technical and just leave the dumb less than sign in there. So then I'd be cube rooting both sides, correct? Cube root, that's 4,000 raised to the 1/3 power. Boom, 15.87. So n plus 1 is less than 15.87. It's very good news. 15.87. And then if I subtract 1 from both sides, I get 14.87. So what's your conclusion? How many terms do I have to add? You can't do 14.87. This is the same logic as our previous remainder theorem, or previous remainder technique. If I do 14, if I round it down, it won't be accurate enough. Does that make sense? I have to round it up. Not round it off, round it up. Even if that had been 14.1, I got to call it 15, right? I need to be more accurate. So I'd have to say and round up to 15. Boom, that's good news, right? Hey, I only have to add 15 terms. All right, I can do that. If there was 700, couldn't do that. But this is converging quickly enough, and perhaps you have the feel of that. Isn't a cubed equation? If that's cubed on the bottom, those numbers get small really fast. And so it's not surprising there's only 15 of them, and I'm as accurate as I need to be. And so, okay, fine, I'll never know the right answer to this, the perfect natural log of pi, some crazy answer that maybe nobody's ever figured out, but I can get it accurate to 3 decimal places after just adding 15 terms. So your assignment will start off with those questions, actually. So I gotta let you go because we're over time, but I find myself kind of going back to that first, wasn't it this one? This is the one we stuck in Excel, right? And we got, what did I say down there? 0.69 something or other. Like we got, that answer right there. Kind of makes me wonder, we had n is 1864 terms and so forth. I find myself looking at that. Let's just quickly do that really quick. Let's take that problem. It was -1 to the n over n. Feel free to take off if you need to, but this will only take a minute or two. So the initial problem, I'll rewrite it with k just so it looks like it's in the same language. It was -1 to the k over k from k equals 1 to infinity. And so what I'm curious about is the accuracy of S of, I'm not going to go back and look, but let's just say 18. Yes, I am going to go back and look. I can't help myself. That was 1864. We found, thanks to Excel, S of 1864. We had 1864 terms, and we're just curious how accurate is that? Is accurate to 2 places, 3? You may remember it looked like it rounded to 0.693. I'm guessing it's 1,000th place just based on what we saw before, but I'm not sure. So let's notice in this case, we know n. This time we know n. We know n. What we don't know is the remainder. We don't know r of n. Does that make sense? Well, it's no different. I say r of n is less than the expression to the +1. Remember, this part of it here is just the alternating part. So I don't need that. An is actually just 1 over k. Remember that? Like the alternating part's not part of the formula, right? We figured that out. Part of the way into our discussion. So it's less than 1 over, not k, but n plus 1. One more than that. And notice this time we weren't cubing it. We weren't doing anything to it. It's just there. Right? There was no other numbers in it. There's no 5 on top, something like that. There was nothing else. That was all there was. I just replaced 1 over k with, well, 1 more than that. All I got to do is solve that then. So let's see, n plus 1, if I multiply it to the other side. Wait, I don't need to multiply it to the other side because we know n is 1864. So we're done. What is 1 divided by? So of course it'd be 1 divided by 1865. What is 1 divided by 1865? I asked myself. It is and it says it is approximately 5 times 10 to the -4th power. So that's 0.000536. In other words, that's how accurate our answer was. So it really was accurate to the 1,000th place, if I rounded it off, or the 5 10,000th place. So we saw that happening in Excel, didn't we? Down there, it looked like this, it stayed the same out to 3 decimal places. That's kind of how we could tell it was working. So we had it that accurate to that point, and there's still some change to go, but we had it that accurate. So if you know n, you can determine accuracy. If you have an accuracy that you'd like to know, then you can actually determine how many numbers you need to add to gain that amount of accuracy. That's kind of cool. All right, get out of here. Stay after if you have any questions. Please bring questions tomorrow if you have them about the assignment. Otherwise, I will
Thanks, Doug.
see you then. See y'all.
Doug.
I had a question from last week's homework.
Sure.
It was number 13 and 15 on 10.3. I was just kind of confused by the answers, well, the correct answers.
I'm pulling that up. I'll share my screen because I can just cheat and stick the answer up there. So you said 13 and then 15?
Yeah. So on 13, I would think that the answer would be just that base. So in your case, I would think that it would be 8, but it turns out that it's supposed to be like 1 less than that. So I think 7 would be the right answer on that one, which I'm not sure why that's the case, because when I write out the terms of the telescoping series, it looks like they just continue to cancel out and just leave me with the first number.
Mm-hmm. Yep, I think I know where you're going with this. Because I had the same. I'm just getting a fresh piece of paper to write that down, and then I'll. 8 to the 1 minus 8. Starting at 1. So we started at 1 for that. So if I put n equals 1 in it, I get 8 to the 1 over 1, which is 8. And then I get 8 to the 1 over 2, which is the square root of 8. So it's minus, let's see, I guess I'll just leave it alone. I'll say 8 to the 1 and 8 to the 1/2. You agree with that? So then n equals 2, I put 2 in there, I get 8, positive 8 to the 1/2, I get negative 8 to the 1/3, and so, okay, cool, I see this is flying now, so I get 8 to the 1/3, 8 to the minus 8 to the 1/4, and so you're saying, cool, so what I see happening is a minus 8 to the 1/2, a plus 8 to the 1/2, a minus 8 to the 1/3, a plus 8 to the 1/3, and so that's just going to cancel forever. And so you're saying, yeah, that looks like it should be 8. And my gut reaction is, I agree with you. Anything you want to add to that? That's what you saw?
No, that's what I saw, and yeah, that's why I think it should be 8, because it's just continuing to cancel out the subsequent terms. But somewhere in there, there's a -1 that sneaks in. I wonder, do you think it's because as n gets larger, you have 1 divided by a large n value, which is really close to 8 to the 0, which is
Yeah.
1?
So again, this would be kind of a fun one to stick in Excel. because, you know, my gut reaction or my initial reaction to this is the same as yours. Genuinely, like I probably would have got this problem wrong myself. So in my little example right there, does it make sense if I kind of said dot, dot, dot here? You'd have like 8 to the 1 over 1753 minus 8 to the 1 over 1754. And those would have canceled out. In other words, this one's still sitting there. Does that make sense? And so you're exactly right. That term is there, if you will. Now, normally that term is gone, like it's on its way to nothing. But the problem is this isn't on its way to nothing. In other words, that term is really kind of minus 8 to the 0 because 1 over 1754 is on its way. So it's not the entire term that's on its way to 0 this time. It's the exponent of that. And unfortunately, 8 to the 0 is not 0, it's 1. And so that's where that -1 is coming from. You're exactly right. And so I think the only place you would actually see that is if you went into Excel instead of approaching 8 like you would think it was, it would actually be approaching 7. And so that would be the proof of it. But again, that still should sort of maybe bother you because it's like, don't all those terms cancel anyway? I mean, the idea that this last term is, if you will, is left over, like, doesn't it always get canceled out by the next term? The answer is kind of yes and no. I mean, that particular term I just wrote would get canceled out by the next term, but the term that is left over, if you will, at the end, if we go to infinity, this last term actually becomes minus 8 to the 1 over n as n goes to infinity. It's the limit of that, technically. So might be fun just for the heck of it real quick.
Okay, so knowing that, number 15 still is kind of confusing because you end up with just the square root of 1 plus n, and n doesn't really grow or really affect it since they are canceling out.
So based on the one that I happen to be looking at, what was your instinctual reaction that the answer to that should be then?
2, the square root of 4, because after that, I'm thinking that the terms should just continue to cancel.
Yeah, so let's take a look at that in the same light. So yeah, to your point, if I start at 1, then I'd have the square root of 4 minus the square root of 1 more than that, that'd be 5. And then I'd have the square root of 5 minus the square root of 6, and bam, then I'd have the square root of 7. Sorry, the square root of 6 minus the square root of 7, so on and so forth. So as you pointed out, if I kind of repair these so that these two are paired, those go to 0, those go to 0, then I'm certainly going to have this 2 left over in the front. But the question is, kind of like the last time, what about kind of that last one that doesn't pair? Well, you're right, like that's on its way to minus the square root of infinity, isn't it? The leftover one, if you will. So again, it's what's troubling about this is, can you always just think of them as pairing and then it just goes away to 0? Because the next one always pairs with the previous one. Or like the last problem, do you have to think of that last one as being left over, if you will? Somehow that's left over and it doesn't get canceled. So I only have 3 terms here. 3 terms of my sum, and that last term is left over. So we're saying, does that, work its way to infinity? So what
Yeah, that makes sense. I think I did at one point when I saw that it was going to be the square root of a small number minus the square root of infinity. I think I did try negative infinity as an answer, which
Yeah.
I don't think that makes much sense.
Well, it's
when I
basically
think of
2 minus negative infinity, which is still minus negative, was still, or the square root of 2 minus the square root of infinity, effectively. Well, the 2 makes no difference, and so it's basically minus infinity, which is why the ultimate answer is doesn't exist. Now that should still bother you some, I guess, is what I'm getting at. It kind of bothers me some. I find myself anytime I can always wanting to kind of, do this manually and say, is that really what's happening here? In other words, thank God that we have the power to visualize this stuff, right? So if I say this equals the square root of, where did that go away? Oh, there it is. The square root of this number minus the square root. Second number. Let's do it this way. Previous number plus 1. So there's the square root of 3 minus the square root of 4.
Unknown caller.
And so there's the square root of 4 minus the square root of 5. And so I can see those getting smaller. But more importantly, we want to know what is the sum equals the sum of this cell plus this cell. And as we drag it down, if we make that. So our gut reaction is the individual terms themselves, notice, are happily getting smaller and smaller and smaller. And what we're really curious about is, does this sum work its way to the square root of 4, which is 2? Is there something wrong with this? I thought it would be. Oh, that's right. This is supposed to be plus 3. This is plus 3 and plus 4, not plus. So notice that you would think that would be working its way to 2 based on what we just did by pencil a minute ago. Seems like it'd be working its way to 2, but everything would cancel. And yet it just seems to be getting sort of, well, at least right now, smaller negatively. Like, to me, it looks like it's on its way to 0 right now. Yet supposedly the answer is supposed to be negative infinity. I don't see that happening yet. Do you?
No.
Why not? If I grab these and drag it down. The individual terms are getting smaller and smaller and smaller, which makes sense. But notice this almost, it looks like it's more like on the way to -1/4. Doesn't look like it's on its way to negative infinity. Drag it down further. Notice this isn't getting bigger, it's getting smaller. The sum is getting smaller.
So almost like it's approaching 0 from the negative side, or
Yeah, or approaching I mean, it looks like it's approaching a limit. Do you see what I'm saying? Like it looks like it's approaching something. It doesn't look like it's approaching some, I was expecting honestly this to get larger and larger and larger
Yeah,
since,
the square root of n+3 or whatever.
yeah, so what the heck is going on here? I'm in trouble. This is not. Something is so wrong with my screen. I cannot navigate this. There we go. Feels like something's wrong here. Square root of that minus the square root of that. Square root of that's troubling me too. Not behaving like it should at all. At least it's not behaving the way that their answer is saying it's behaving. One of the issues we have is the number is so small. I'm just dragging this even further down just because I'm hoping to have a brainstorm of some sort that isn't as of yet not happening. Still getting smaller. I'm looking at just the last two numbers and it goes 11, and then it goes 477 instead of 4, then it goes to 407. I'm not happy at all.
Yeah, maybe it's just the formula.
Minus. Well, I mean, part of it might be the fact that it's, it's just saying it's saying to evaluate it. And, after going down to many terms, like our ability to evaluate it, we're not able to evaluate it because it's still changing down there after 5,000 terms. And so it certainly isn't going to 2 like we kind of, like, as you said, we might have thought it would. Wow, I'm embarrassed to say that's actually bothering me a lot.
Is there a quiz coming up?
No, I didn't make quizzes for this class, so everything that you're doing in here is just the homework assignments and the tests that we take, so.
Okay.
I'm gonna have to think about that a little more.
Yeah, maybe later I'll put it into Excel and see if I can, or